Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will emphasize and accentuate on one important topic of discussion, which is the conversion of a galvanometer into an ammeter and a voltmeter. Number one, we will focus our attention on an ammeter. So, an ammeter is nothing but an electrical instrument which is used for measuring electric current. And this ammeter is always connected in series in any electrical circuit for determining the magnitude of the electric current. Now, what are the emphases which are laid down for the conversion of an ammeter, for the conversion of a voltmeter into an ammeter? Now, for you to convert a galvanometer into an ammeter, you have to connect a low resistance resistor. That means in this case, if I have a connection in this form, that means over here, this low resistance resistor, let this low resistance resistor be connected in parallel to this galvanometer. This low resistance resistor which is connected in parallel to the galvanometer, this low resistance resistor which is connected in parallel to the galvanometer, this is what we define as the shunt resistance. Okay, that is why over here I have written as S. And over here, let the resistance of this shunt resistor, okay, let the resistance of that shunt resistor be Rs. Okay, let the resistance of that shunt resistor be small rs. So from here, very important point that you need to note down in the exam is regarding the definition of shunting. What is this shunting? Shunting is nothing but a process in which you connect a small resistance to a galvanometer, and this small resistance is connected in what? In parallel here. So we have this low resistance resistor. It is a low resistance resistor which is connected in parallel to a galvanometer. So from here we have to devise certain things in order to find out the determination of the resistance. First point that we need to note down over here is that we need to determine the resistance of this shunt resistor. So which means that if Rs is the resistance, if Rs is the resistance of this shunt resistor, which means that we need to find out what will be the formula for the value of Rs. So likewise in this case, we will put certain conditions which we need to find out. Suppose from here, let I be the current in the main circuit, and the current, part of the current will flow through the galvanometer. Then let us initialize that current as Ig. Okay? Let us initialize that current as Ig. Then if we apply those Kirchhoff's current law, which means that this point over here, this is the junction point. So the current with respect to this junction point over here, this current I is approaching this point, and this current Ig, it is leaving that particular point. So the remaining current will flow across this branch. Across this branch, passing through the shunt resistor. So from here, since this current I in the main circuit is approaching this junction point, is entering that junction point, that current will be taken as positive. So with respect to that junction point across the shunt resistor, we find out that this Ig is leaving this junction point. This Ig is leaving that junction point. So that is why the current which flows to that network or to this branch, okay, will be what? Will be I minus Ig. And similarly, this current Ig flows across this branch, and this current over here also, this will be what? This will be Ig. Then, if you keep on applying the Kirchhoff's voltage law, that means at this particular point, this is also a junction point, then we find out that this current is approaching this point, and this current is also approaching this point. That means we want to find out what will be the current across this branch. So from here, first current, we have that, if you look with respect to this arm, if you look with respect to that arm, that means it will be the current across that branch will be what? I minus Ig. And with respect to this point, another current is approaching this junction point. All this current is also approaching this point. This current is also approaching this point. Then all the currents entering the point will be taken as what? Will be taken as positive. So from here, if you work out the math, that means this will be negative Ig, this will be positive Ig. So things gets cancelled, so the current over here will be I, which means that the current in this case also will be I, which is the current in the main circuit. So that satisfies the verification of Kirchhoff's current law. Okay, Kirchhoff's current law. So in this case, let us write down some of the important contexts. So over here, let Rs be the resistance of the shunt resistor, and then over here let Rg, okay, capital Rg, be the resistance of the galvanometer. Then over here we will put let I be the current in the main circuit, and let Ig be the current through the galvanometer. Then from here we find out that we have to find the potential difference across this galvanometer. So what will be the potential difference across this galvanometer? That means the potential across these 2 points. Okay? These 2 points of the galvanometer. So if you want to find the potential difference to these 2 points, that means if you multiply the resistance of the galvanometer, if you multiply the resistance of the galvanometer, what is the resistance of the galvanometer in this case? It is Rg. Okay? This is the resistance of the galvanometer. And if you multiply with this current which is flowing through the galvanometer, that means that current Ig, that means Ig into Rg, this will give what? This will give the potential difference across the galvanometer. Suppose let Vg be that potential difference across the galvanometer. Then from here, this we will do just the writing from what we have learned. Okay, so the using Kirchhoff's current law, the current I minus Ig, okay, this current I minus Ig, it passes through the shunt resistor. So this current, it passes through this shunt resistor S. So you need to find the voltage across this shunt resistor. So similarly, the voltage across that shunt resistor, it is the product of the current and the voltage. So what is the current across this shunt resistor? The current is I minus Ig. So that is the current across the shunt resistor. And what is the resistance of the shunt resistor? It is Rs. So you need to take that value of Rs and then put over there Rs. So which means that this will be what? This will be the voltage across the shunt resistor. So over here, let me write this as Vs. Okay, let me write that as Vs. So from here, another important assumption is that when the galvanometer, okay, when the galvanometer and the shunt resistor, which means that the voltage drop, when the voltage drop across the galvanometer and the shunt resistor are in parallel, that means the voltage across them will be what? Will be equal. So this is very, very important to note that when you connect devices, any devices which are connected in parallel, I have the galvanometer which is connected here, and I have the shunt resistor which is connected here, which means that the PD across the galvanometer and the PD across the shunt resistor should be equal. They should be equal, which means that when I say PD across the galvanometer, that means Vg is the PD across the galvanometer. This is that equation which satisfies. And over here, what will be the PD across the shunt resistor? The PD across the shunt resistor will be what? Will be that Vs given by this equation. Okay, given by this equation. So from here, that is the most important concept. That means over here we can write down that in such condition, when appliances are connected in parallel, that means their voltages or their potential are equal, which means that over here, what is Vg? Vg is what? Vg is this Ig, Ig, Rg. Okay, Ig, Rg. And what is this Vs? This Vs will be I minus Ig bracket. This will be Rs. So we want to find the magnitude of that shunt resistor S. Okay, shunt resistor S. So from here we will keep this Rs this side, and then we will cross multiply this bracket to the left hand side of that equation. So over here this will be Ig, okay, Rg divided by 1 divided by I minus Ig. So this is the expression for what? This is the expression for the finding the resistance of the shunt resistor. So that is the expression for finding the shunt resistance. So this will give you that formula for finding the resistance of the shunt resistor. Okay? Finding the resistance of the shunt resistor. And this, after you solve, that means it should be recorded in ohms. Then from here, total resistance. When you are asked to find the total, so this will be the ammeter. Before we move on into that discussion, this is an ammeter. So ammeters are of different types available in the lab. What I have showed over here is a mini ammeter. So we have ammeter. We have different range of ammeter. We have ammeters which are written as A. We have ammeters which are written as MA in this form. Okay. We also have ammeters which are written as UA. So the importance of this is that when we are talking about MA, okay, 1 milliampere, okay, you should know that this will be equal to what? 10 to the power minus 3 amperes for 1 milliampere. And another context of 1 microampere, okay, 1 microampere, this 1 microampere, the value in terms of its corresponding ampere will be 10 to the power minus 6, which if you look at this particular picture, that means from 0 up to 20, okay, over here this is 20, from 0 up to 20, that means from here up to here, from 0 up to 20, there are 10 divisions, okay, 1, 2, 3, 4, this is the 5th division, 6th division, 7th division, and 8th division, which means that over here, this you need to find out how much is the least count of that particular value. So from here, since there are 20 divisions, from here, which means that that 20, 10 divisions in that case, okay, there will be 10 divisions in that over here from 0 up to 20. This is 20. Let me write down over here. This is 20. From 0 up to 20, there are 10 divisions, which means that for 10 divisions, it will be equal to how much? 20 milliampere. Then you want to find out how much is that small division over here. How much is that small division? Which means that one div. One division in this case will be 1. Cross multiply this 10 this side. Okay, cross multiply that 10 that side. That means this 0 and this 0 gets cancelled. Which means that that small division will be equal to 1. 2 amperes. Okay? 2 amperes. Which means that if you enlarge the figure over there, if you enlarge the figure over there, that means this will be the 0, okay, the 0 end, and over here this will be 1, 2, 3, 4, the 5th division, 6th division, 7th, 6th division, 7th division, 8th division, 9th division, and the 10th division. This is 0 and this will be 20, which means that this division over here, that division over there, that means this division will be equal to 2 milliamperes. Then this is your milliampere range. Then over here this will be 1. Each division will be equal to 2. That means 2 plus 2 will be equal to 4. Then 4 plus 2 will be equal to 6. This will be equal to 8. This will be equal to 10 milliamperes. So on and so forth. 10 plus 2 will give you 12. And then 12 plus 2 will give you what? 14. 14 plus 2 will give you 16. And 16 plus 2 will give you 18. 18 plus 2 will give you 20. So this is the way how to find out the graduations in your milliammeters in your ammeter. So preferably in the lab, you have 3 sets of ammeters, one with ampere range, the one with milliampere range, and the other with microammeter range. So another important point that we need to focus and ponder here is that you need to find out the total resistance of the galvanometer. So over here we have 2 points. first point is that this galvanometer is connected in parallel, and this low resistance shunt resistor is connected also in parallel, which means that we have, in order to find the resistance of an ammeter, that means it should be what? It should be the parallel combination of the given resistors. So which means that if I say that let the resistance of let Ra be the resistance of the ammeter, since they are in parallel, so that is why the formula for parallel combination of resistors will take place. So from here we'll have 1 by Ra. So it will be partly the resistance due to the galvanometer Rg, and partly the resistance of one of the shunt resistor, which means that if you work out the math from here, you will get here Ra, this will be equal to 1. This will be equal to Rs Rg divided by Rs plus Rg. So this is our equation. Okay, this is our equation. So from here, let us do some analysis. Suppose let us consider, when you look at this denominator term of this equation, we have this factor of Rs plus Rg. We know that by definition, this resistance is very, very low, and the resistance of the galvanometer is quite higher. Okay? It is quite higher. So in this case, if the resistance of the galvanometer is very, very large in comparison to the shunt resistor, which means that this denominator term, Rs plus Rg, this denominator term will be approximately equal to the highest quantity. That means we can neglect that Rs. Then we have, it is simply equal to Rg. It is simply equal to Rg. So which means in that case, that means over here, okay, if Rs is equal to Rg, okay, if Rs is equal to Rg, which means that in that case, okay, in that case, which means that if you look with respect to this condition, if you look with respect to this condition, that means from that, if I mark this as one equation, that means mark this as suppose equation star, that means that equation star reduces to, that means the resistance of the ammeter will be equal to what? Will be equal to Rs, the Rs Rg divided by 1, divided by Rg, because this result holds true. Then from your Rg and Rg cancel, you get equal to Rs, which means that in this case, the resistance of the ammeter is equal to the shunt resistance. So in such cases, the resistance of the ammeter is very, very small, almost equal to what? Almost equal to the shunt resistance. From here, this is the concept. Okay, this is the very important concept, that the resistance of the ammeter Ra will be equal to 1, will be equal to Rs. Since this Rs is what? This Rs is very, very low, and that is why for finding the current in any electrical device, the ammeter should have what? Low. The resistance of the ammeter should be very, very low. Okay? The resistance of the ammeter should be very, very low, so that you can measure the current with greater accuracy. Then we will move on into the next device, which is your voltmeter. So a voltmeter is also another important instrument in the physics lab, whereby you have to measure the potential difference. Okay? You have to measure the potential difference across any conductor carrying a current. And from here, how can you convert? Okay, this is very important. How can you convert a galvanometer into a voltmeter? So we can convert this galvanometer into a voltmeter by connecting a high resistance resistor, but this should be connected in series. Earlier in ammeter we connected a low resistance, but in this case in voltmeter we connect what? We connect a high resistance in series. Earlier for ammeter it is a low resistance in parallel, but over here in case of voltmeter it is a high resistance in series. So from here, that means we have to put certain assumptions. That means from here, let capital R be the resistance of be that high resistance which is connected in series. This is the figure, and this is the circuit diagram, I mean. And from here, let Rg, let Rg be the resistance of the galvanometer, and let suppose Ig, okay, and let Ig be the current across the galvanometer. Okay, let Ig be the current which is flowing through the galvanometer. Okay, through the galvanometer. So over here we have this current Ig which is flowing through the galvanometer, and it flows, okay, in that direction. Okay, so this also will be one current. Then from here, how will you find the total resistance? So over here, you know that this is the combination. This is the circuit diagram. That means this is the circuit diagram which makes what? Which makes a voltmeter. That means the voltmeter resembles this circuit diagram. Okay? Partly earlier, that means what we have learned over here is that this the circuit diagram over here, this which we have note down over here, this is the circuit diagram. This is equivalent to what? This is equivalent to the circuit diagram of an ammeter. So an ammeter is nothing but it is represented by this circuit diagram. So this whole circuit diagram over here, this whole circuit diagram, and over here also that circuit diagram with respect to a voltmeter. This is that circuit diagram. Voltmeter, high resistance resistor connected in series. So if things are connected in series, the galvanometer also will have resistance. This high resistor also will have resistance. Then what will be the value? That means over here let we will put an assumption that in order to find the resistance of a voltmeter, then we will put an assumption that let RV be the resistance of the galvanometer. Since they are connected in parallel, so RV will be the series combination of these resistors. So partly there will be the resistance of the voltmeter and partly the resistance of that high resistor. So what is the resistance of this G? The resistance of that G is Rg. And what is the resistance of this high resistor? It is that capital R. So over here we will write Rg plus R. Okay? Rg plus R. Then from here we will need to find the resistance of that series resistor. Okay? So very important point to note down here is that when the high resistance is connected in series, okay, then this is your voltmeter. Okay? This circuit arrangement is this voltmeter. So from here, when the high resistance, okay, when the high resistance is connected in series, so when this high resistance is connected in series with the galvanometer, the current flowing through the galvanometer, okay, is the same. Which means that what does it mean over here? This is very important. Which means that if Ig is the current, which is flowing across Rj, then this amount of current also flows through what? Flows through that high resistance resistor, which is your R. So Ig also will be common to capital R, which is our high resistance resistor, and Ig also is common to G, which is the galvanometer. From here, let us write down the equation. Then using Ohm's law of the potential difference V, okay, using Ohm's law, the potential difference V of the voltmeter will be equal to what? Will be equal to Ig. Then within bracket we have the resistance of the galvanometer and the resistance of that high resistor. Okay, high resistor. So from here, if we solve the math, okay, we will get this Vg divided by V by Ig cross multiply this side, and we'll have this to be what? Rj plus R. Okay, Rg plus R. So from here, if you want to find, it's very important, if you want to find the resistance of the series resistor. So what is the resistance of that series resistor? It is capital R. So capital R will be question mark. So how will you find capital R from here? That means you just do some simple algebraical steps. When you carry this RG to the left hand side, okay, when you carry that RG to the left hand side, so over here I will write in this form VG or V divided by IG, carrying this RG this side, so the sign will be minus RG. And over here we have only what? We have only capital R. So that expression will help. This is that expression for determining, okay, determining or finding the value of the resistance of the series resistor. Okay, so this is the expression which gives the resistance of that high resistor, which is connected in series with respect to the galvanometer. So another important thing is that you need to study also the sensitivity. When I talk about the sensitivity, that means how perfect a device can be operated. So this voltage sensitivity, or also we have learned about current sensitivity. When we talk about sensitivity, is nothing but the voltage, the deflection per unit voltage, which means that over here, if phi is the deflection and capital V is the voltage, which means as per this definition, voltage deflection per unit voltage, that means phi divided by V. This is what we define as the voltage sensitivity, SV, the voltage sensitivity. So we have learned from while deducing the relationship of current through a galvanometer, we have come across this expression. Okay, we have come across this expression that we write down. I will be equal to what? I will be equal to NAB. Okay, I will be equal to NAB divided by 1 divided by K. This will be equal to 5. So that is our expression. Okay, our expression. So what is this NAB divided by 5? Also we have write down that this will be equal to G, and this G is what we define as the galvanometer constant. Okay? This G is our galvanometer constant. So from here it is very important that if you look with respect to this aspect, okay, or if you look with respect to this aspect, that means the current sensitivity. The current sensitivity always it is written as 1 phi divided by 1 phi divided by I. So this phi divided by I, okay, this phi divided by I will be equal to 1. Phi divided by I will be equal to NAB, okay, NAB divided by K, okay, NAB divided by K. Over here, there is some something is wrong. Okay, let me do some correction. I equal NAB divided by K. Okay, I equal, no, it is not NAB divided by K. It is, this will be equal to K divided by NAB. So this is our expression, K divided by NAB. So this is the value of our Galvanometer constant. So phi by I, if you make use of this equation, phi by I will be equal to what? Cross multiply this side, cross multiply this side. So we will again I'll write as capital N, E is the area of the coil and B is the magnetic field. NAB divided by K. What is this K? This K is your torsional constant. Okay? Torsional constant. So this is your current sensitivity. How will you find voltage? Okay, how will you find voltage? So from here, this is our phi. That means if you cross multiply I this side, that means you get what? You get NAB divided by K into I. Then next, from that step, we will divide both sides by V. We want to get this. This is the expression for SV. SV is voltage sensitivity. Voltage sensitivity is phi divided by V. So over here on this expression we have phi, so we will divide both sides by V. When we divide both sides by V, that means we'll get the voltage sensitivity. Over here we have NEB divided by 1 divided by K, and over here we have that I divided by V. When you look at this term, I divided by V, this I divided by V, okay, let me write here properly, this will be phi divided by V, this will be 1, this will be NEB divided by K, and this I divided by V, it is nothing but the reciprocal of what? The reciprocal of your resistance. So this expression over here, this expression is nothing but one, the voltage sensitivity, in which in that case I have denoted by one, I have denoted by SV. So this is the expression for the voltage sensitivity. Okay? Voltage sensitivity. Then another important special case from here is that suppose if the number of turns is double. Now what happens? Then the resistance also will get double. So which means that over here, if we have, if n is, if capital N is the original number, okay? If capital N is the original number of the number of turns in that given device of a voltmeter, then when I say if it is double, that means it is 2 times of n, okay? 2 times of n. So 2 times of n, this will be what? This will be the new number of turns, which I will write as n dash. Let n dash be the new number of turns. When the number of turns is double, the resistance also will get double. On what idea? Because resistance is directly proportional to the length. You also have learned that resistance is inversely proportional to the area of the section. Based upon this hypothesis, which means that if number of turns is double, then if R is the original resistance, and when you double that R, that means twice R, that means this new resistance R dash will be equal to twice R. So which means from there, that means if you study the new current sensitivity, okay, new current sensitivity, so that new current sensitivity will be what? Phi divided by V. So let that phi divided by V be the new current sensitivity, phi dash. Okay, so this will be what? This will be SV dash. Then from here, which means that when you substitute on this equation, that means this n, in place of this n, that means you will write by what? You will write as twice n. And first, before writing that twice n, that means let us write properly. That means in place of that n, that means this new will be n dash. And over here, the resistance, okay, over there, the resistance will be what? The resistance will be double. Okay, so in this case, we have like that, and in that case, the resistance, this resistance will be what? Will be the new resistance, which is your R dash. From here, all those other parameters remains the same. That means we have the area, we have the magnetic field, we have this torsional constant, and then value of 1. So when you look in that particular equation, you will find out that this n dash, what will be n dash? N dash will be twice n. So you put over here twice n, and over here this will be n, a, and b, and over here this will be k. But when you look, what is this R dash? R dash also the new resistance will be equal to twice R. But when you look from here, that means these values, these numbers, okay, these coefficient 2 and 2 will be cancelled, which gives us the result that this will be NEB divided by K into 1. This will be 1 by R. So this will be what? This will be phi divided by V dash, which means this is your current sensitivity SV. Okay? Current sensitivity SV dash. So our current sensitivity SV dash, that means when you look with respect to that equation above. Okay, when you look to this equation above, when you look with respect to this equation above over here, that means over here you have NAB divided by K into 1 by R. NAB divided by K into 1 by R. What is this equation? This equation will be equal to SB, which means that it remains the same. Okay? It remains the same even if you double, which remains that the current sensitivity, even if you double, that means it remains the same. Over here, that means the current sensitivity, the voltage sensitivity, I mean, the voltage sensitivity, the voltage sensitivity, the voltage sensitivity remains the same. Remains the same. When what? When R is twice R, such that under the condition that N is double. Okay, so the voltage sensitivity will always be the same. So these are some of the relevant proofs pertaining to the special cases of voltmeter. Just go through the important lecture right from the beginning so that you will understand the concept. Thank you.